name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunications Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to the RF seminar number 12. Today's talk will be on measuring the effects of RF interference in radar receivers. This is work that has been done by myself, Frank Sanders, and then Bob Soule of OSM in Washington, John Carroll here at ITS, and Brent Bedford here at ITS. And so this particular talk is attributed to all of us. Now, what motivates this? What motivates this is that although radars have historically been allocated in bands where they have not shared spectrum with non-radar systems, basically with communication systems, in recent years various proposals have been made to operate non-radar systems, generally communication systems, in radar bands. Typically, these have basically broken down into the following broad categories: radio local area networks, RLANs, and various proposed mobile radio systems. Generically, right now, they're called by people who are working in the area IMT 2000, IMT Advanced, WiMAX also actually would now fall into this category also. And because people want to put these non-radar systems into radar bands, these proposals have really raised the question: at what thresholds do various types of radio interference cause degradation to the performance of radar receivers? We need to know this so that if radar systems are going to try to share spectrum with these other types of systems, we can do electromagnetic compatibility analyses where we can plug in the threshold or thresholds where the radars might start to experience degradation when we're trying to compute separation distances or coordination distances, etc., between these systems, and if we're looking at the whole question of the feasibility of these systems overall in terms of sharing spectrum with radars. Now, the last talk had a slide very similar to this, so I'll cover this quickly, but I did want to discuss just the basics of classical tube-type microwave radars and then advanced solid-state radars, because it's important to understand how these radars are currently sort of occupying the spectrum when we're looking at other systems that might try to share spectrum with them. First of all, microwave radars typically are transmitting pulses at an EIRP, that's the radiation level as measured in space outside the antenna, peak EIRP of a little over a gigawatt for a typical medium to long range radar, air search radar. Now, if there is anything typical about radar designs for classic tube-type microwave radars, it is that for a medium to long-range radar, as we discussed in the last talk, the radar pulses are typically on the order of a microsecond long. The listen time between the pulses is typically on the order of a millisecond, so these radars are typically operating at a duty cycle of a microsecond divided by a millisecond, which is 0.1%. And this means that they're operating as passive sensors about 99.9% of the time. So here we've drawn schematically the time behavior of a radar transmitter where the pulse is fired at time equals 0. This is a microsecond long pulse. Then the radar receiver runs, limited only by its own internal noise, listening for echoes, and then a millisecond later the next pulse is fired. And back in talk number 6 we of course discussed why that kind of time interval would be picked for a medium to long range radar. And so given that between the transmitted pulses they're operating as passive sensors, as passive receivers, that means that the operational performance of these radars is somehow going to be limited by their own internal receiver noise. And this means in turn that external factors that add power, add energy to the radar's internal noise level will somehow or another have to tend to degrade the operational effectiveness of the radar. Now, for solid-state radars, and again we're copying or we're repeating a little bit of this from the last talk, for solid-state radars, sometimes just called advanced radars, We're operating with power levels that are a tenth, roughly, of what they would be for a tube-type radar, with pulses that are commensurately 10 times longer, because you have to get the same total amount of energy inside the pulse if you're going to get a detectable echo back. But this means that the peak EIRP coming out is still going to be something on the order of 100 megawatts. Again, if there's anything typical about these radar designs, it might be that for a medium to long-range radar, we'd be looking at 10 microsecond long pulses. But here's the catch. The repetition interval between the pulses still has to be 1 millisecond, because that's governed by the radar range requirement. And that means that we tend to get higher duty cycles with these radars. Nominally, we'd get a 1% duty cycle, but there are some of these advanced or solid-state radars who are getting up to a 10% duty cycle. And yet, to maintain range resolution, where the pulse width is really long, some kind of change has to be implemented in the radar design, and that change is coding either in frequency or phase inside the radar pulses in order to retain range resolution, which you'll recall is governed by the pulse length or the pulse width. And this higher duty cycle, this 1 to 10% higher duty cycle, does have implications for the electromagnetic compatibility between advanced or solid-state radars and other radar systems that are sharing the same band. As we'll see, radars tend to be fairly compatible with each other in a band. So, quickly on the pulse coding, because again we discussed this briefly in the last talk, we can either code in frequency, in which case while a pulse is being fired, say this is a 10 microsecond long pulse, we could ramp the frequency up, or we could ramp the frequency down, or we can change the frequency in some nonlinear fashion with time. And when the pulses are received, the receiver has time-dependent, the receiver has frequency-dependent delay lines, and these frequency-dependent delay lines result in pulse compression in the receiver, which is effectively processing gain, receiver processing gain, which gives us our range resolution back. I'd also like to point out, and I would have actually liked to have pointed this out in the last talk, that the chirping behavior is also used in classical radars for performing elevation scanning while the radar antenna rotates. We saw the SPS-48C in the last talk. Now, it is true that for a small frequency change, the behavior here in terms of how the beam gets elevated vertically to get a 3D effect on the radar while the antenna is rotating, operationally that's almost indistinguishable in some cases from just doing phase shifting on the array face. But it's just worth noting here that that is one application of chirping in classical radars. So as I say, this frequency modulated set of transmitted pulses results in a set of frequency modulated echoes coming back from targets. Those echoes are compressed in the receiver, and we get back the range resolution that way. The other way of modulating the pulses is in phase, and you can either do discrete 0 to pi transitions, which is what I've drawn here schematically, where we're shifting phase while the pulse fires, or we can do continuous minimum shift keyed variations. In any event, whichever way you do it, the phase coding, which can also be used in classical radars to improve the performance of the classical tube-type radars in high clutter or jamming environments, in the solid-state radars does result in, processing in the receiver that compresses the pulse echoes to regain range resolution. Basically, the effective range resolution of a radar like this is the width of one of these chips. And again, this basically is a methodology for getting gain in receiver on the pulse echoes. And there are 13 chip or 13-bit series of pulses that lend themselves well to this. They're named after Barker. They're called Barker codes, and if you do see radar pulses that have a length in microseconds that happens to be evenly divisible by 13, so either 13, 26, 39, 52, etc., there's a good chance that they're actually doing Barker coding. That's if you don't have a VSA to pull it apart. If you do have a VSA, you can see that directly. Now we come, though, to the problem of what about interference? So we go back to the first drawing that we did. We'll just look at a classical tube type radar. The same physics apply to the solid state radars. We fire a short pulse, we wait, we run as a passive receiver 99.9% of the time. We're limited by the receiver's noise level. And you'll notice that there's a second line that I've drawn in here, a red line. I've drawn that as a detection threshold. That is a schematic. It's drawn so that we can visualize the idea that there's some kind of a threshold where if we can detect a target echo above that threshold, we can say, okay, we'll declare a target. Bear in mind that because the echoes from the radar targets are so weak, and we saw that in talk number 6, typically the target echo level is below the radar's noise floor. That means that we typically have to run 15 to 20 pulse echoes from a target. That means we have to get echoes back from 15 to 20 of these pulses in order to integrate enough energy to cross a detection threshold and get a detected or declared target. Now, that also means that any interference energy that gets into that receiver that raises the radar receiver noise, and you could say by any amount, but as a practical matter, we could say by half a dB, and we'll see support for this statement later in the talk. Anything that can raise that noise by, say, a half dB or more in the radar's receiver can therefore cause a desired target to effectively fail to be detected. We've drawn this schematically here. We've got some target echoes that are below the level of the noise, but we integrate 15 to 20 of these pulses. We're able to integrate an echo back out, but now on this target we have some interference that occurred in here. That radio interference raised the level of the radar's internal noise in its receiver, and that schematically can cause us to lose a target. Now, in order to get a half dB rise in noise floor, if we're doing straight power summation, the math gives us about a minus 10 dB interference noise ratio. That is, if the interference power over here is down around, say, this level, 10 dB below the radar's internal noise, then, as we'll see on the next slide, the result is that the summation of the radar's internal noise power and the interference power is half a dB. So here we've plotted the interference plus noise power divided by the radar's receiver noise power as a function of the ratio of the interference to noise in the radar receiver. So if we have a minus 10 dB I over N, we can read up like this, and we see that it's roughly a half dB of I plus N over N. So we're seeing the function of how much the internal noise gets raised in the receiver as a function of the I over N ratio. Once the I over N ratio gets to 0, of course we get a 3 dB increase. That's easy to do in your head. And once the I over N ratio gets to about 10 dB, then I plus N over N converges to I over N. So if you're looking at I over N's of 10 dB or more, you can pretty much you can pretty much say that I plus N over N equals I over N if the I over N is 10 dB or more. On the other hand, if a radar receiver is getting an I over N of 10 dB, it's, as again we'll see here on some subsequent slides, it's wiped out on that particular azimuth where the interference is getting in. So this is a nice handy little graph that you can use. One quick aside, sometimes people do ask, well, are these radars really using their spectrum allocations anyway? This is an example of a high-powered naval air search radar running in the spectrum between 3100 to 3700 megahertz. This is a radar that uses a lot of spectrum in there, and the answer is yes, radars do use the spectrum. The trouble is usually when people look for these radar transmissions, they are using techniques or methodologies that do not lend themselves to picking up those very, very short, low-duty cycle radar pulses. And so when people use a poor methodology and they don't see the radars, they typically say, oh, the radars don't seem to use the band, but that would be naive. If they use the techniques that we use in NTIA spectrum surveys, and we'll talk about this in a later talk where I'll show results of a typical NTIA ITS broadband spectrum survey, they'll see that yes, the radars are in there. The radar duty cycles are low, typically 0.1% duty cycle for a classical radar, 10% duty cycle or so maybe for a solid-state radar, but they are in there. So if you do a properly configured, what I would call properly configured spectrum measurement, yes, you will see that the radars are in there. Now, given the concerns that I've raised, given the way that the radar transmitters and receivers work and their apparent mathematical vulnerability to interference, we come to our radar interference research program that ITS and OSM started back about 8 years ago. And what we needed to do was address the lack of quantitative data that existed at that time regarding the thresholds at which different types of interference would degrade the performance of different types of radar receiver systems. And it's hard to set an exact start date, but we started in earnest on this back in around 2001, 2002, working jointly in NTIA between ITS and our sister agency, OSM in Washington, D.C., to undertake a joint effort to determine this information. Now, we needed to do one thing first, which was to come up with an interference criterion. We've already referred to interference to noise ratio, and this is a little different as a criterion from what we might look at in communication receivers, where people look at a desired signal level relative to interference, or a carrier level relative to interference. In radars, there is no really desired signal level or carrier level per se, although Bob Achatz would argue that you actually can do the conversion, and I'm convinced you're right, Bob, you can do this. You can come up with an equivalence, definitely. But because radars are noise limited, we decided to go with an interference to internal receiver noise level criterion. And we've never been able to think of anything better. People have said, is there anything better? We've said, if anyone else can think of anything, we're all ears. We have never been able to think of any better criterion. All right, so if we're going to use that as the interference criterion, then what is our metric for radar receiver performance at a given I over N level? And so here we come to the idea of determining the radar performance in the presence of a particular I over N by injecting controlled targets and looking at the probability of detection of a set of controlled targets. There wasn't a lot of existing work on this, so to a large extent we developed this idea ourselves. Again, we haven't really come up with any better methodologies for this. The basic approach is to say that we will inject some controlled desired targets, and then we'll count them as we raise the I over N level. The reason that we wanted to go with injected targets is that we need to have a good solid baseline count on these targets when we are not injecting interference, against which we can compare the effects when interference is being injected. Now, as a professor who I used to have over at CU named Nauenberg used to say, you realize that we're talking about frictionless elephants here. Yes, we are. Real radars operate in clutter environments. Real radars will try to develop tracks on targets. Real radars have a harder time finding a target initially than tracking it from scan to scan. But we have to somehow simplify this problem down to something that allows us to compare the performance of the radar with and without interference while we're holding other factors constant. And so what we hold constant is the target injection. With that said, we have done live target testing where we've looked at aircraft that are flying in the air, and we have done some testing where we actually radiated the targets into the radar. We got similar results, but those tests are very, very difficult to do. So we do a baseline non-interference probability of detection where we put targets in like this. This is a set of targets being injected into an air traffic control radar, and we get them strong enough by basically just adjusting the power of their adjusting the power level of the targets going into the receiver in order to get them up to a high percentage. We decided on 90% for a baseline level. That actually is a strong radar target. Some criteria that people have for some radars calls for 80% PD for performance testing of radars. So when we go to a 90% baseline probability of detection, that's detecting targets, no interference. Those are nice, strong targets. That means that if anything, we're skewing the results in favor of letting more interference get into the radar before we would see a particular effect, because we're making the targets really strong. We're trying to make them hard to interfere with in a certain sense. So the basic procedure is as follows. And by the way, this is a photograph of Bob Soule of OSM up on a tower with a maritime radar, and we actually are coupling the interference and the targets into this radar on a hard line, and because the entire radar is contained in this box up on the mast top, we saw one of these radars in the last talk that I gave last week. We actually had to run a line up the mast and couple it in there, and that turned out to be a trickier process than we had envisioned, but we did it. So here's what we do. First, we disconnect the radar receiver from the rest of the radar, and we inject, well, we disconnect the radar receiver that is from the radar antenna, where it would be getting received echoes in space through the antenna. And in place, or in lieu of the connection of the receiver to the antenna, we inject, usually on a hard line, desired or controlled targets at radio frequency, so that they will get handled by the radar receiver as if it were seeing regular echo returns.
Now, the transmitter's totally disabled at this point? Or?
Good question, Bob. Is the transmitter totally disabled? Sometimes yes, and sometimes no. It depends on the radar. Sometimes we have to let the transmitter run because the radar receiver is smart enough to know that we pulled the power on the transmitter. Mm-hmm. If we can get away with pulling the power on a transmitter, we will, because we don't need the transmitter. And it does simplify things some. But this was a radar that was smart enough to know when the transmitter was disconnected. So we actually had to keep the transmitter running. Now, you can also run the transmitter, however, into a dummy load. Having said that, you don't have to run the transmitter into the antenna either. Mm-hmm. This also gets into the packaging of the radar and how you can get in here. And one other thing in that vein, Bob, is no two radars are alike, and the people at the site have to use some ingenuity with every single one in terms of literally scratching your head and saying, how does this radar work, and how can we break into it, and how can we do this? Then, having broken the connections, though, like I said, and like you say, either disabling or running the transmitter into a dummy load, dealing with how the receiver sees the transmitter turned on or not, then we get the targets going, the desired targets, no interference yet, just the desired synthetic targets, and we run them up and down in power, and we keep counting them scan to scan to scan until we come to a 90% probability of detection for those targets. Typically, by the way, we count 200 injected targets at a time. We look at how many were actually counted, and we try to come as close as we can to seeing 180 targets out of 200 injected. So it's a bit of a time-consuming process, especially if you have to count them by hand, but we do. Having gotten that level, we can then hold that baseline level on the targets and then begin to inject interference into the radar, also at the RF stage, also into the receiver. We can pick our modulation, and then that power level might typically start at an interference noise level of -12, where most, if not all, radars, with the possible exception of one meteorological radar, were not affected, and then gradually step the power level up to -10, -9, -6, etc. By the time you get up to 0, +3, and +6, usually you've really wiped out the ability of the radar to see any desired targets. We do these increments because they're large enough to get a lot of data points fairly fast, but they're small enough that we can generate a good curve, as we'll see, of probability of detection as a function of I over N ratio. Now, having said all that, there's one type of interference that we have run up to as high as +60 dB, which admittedly was actually done that particular time by accident. And that is if we're running in interference that replicates another radar with a low duty cycle. It turns out, and we'll see why in a minute, that radar receivers can see other radar energy up to levels of +60 dB if the duty cycle of that radar energy is 1/10%, and still detect desired targets through that, as opposed to what happens with the comm signals, where the comm signal, by the time you hit 0, +3, +6, you pretty much wiped it out. As I said, we counted 200 desired injected targets for every data point that we took. So, for example, if we're using, let's say, CDMA modulation for the interference, we'll turn on the CDMA interference at a level of, let's say, -6, count for 200 desired injected targets, and see how many we actually get, and take the ratio of how many we actually see divided by 200 as the probability of detection when CDMA interference is coming in at, let's say, a -6 dB level. Modulations that we used were carrier waves, which are nice as a kind of a baseline, CDMA, TDMA, BPSK, QPSK, OFDM, electronic news gathering, outdoor broadcast, that's ENGOB, and ultra-wideband signals. We didn't necessarily put every type of interference modulation into every type of radar for various reasons that had to do with what types of interference we thought might potentially eventually occur in various radar bands, but we used a number of these interference modulations on every radar that we tested. Now, here's a schematic block diagram of our system. So here we have the radar antenna with a transmit-receive switch. This can also be a circulator, but I've drawn it here as a mechanical TR switch. It could also be a pin switch, which on one side is connected to the transmitter, on the other side connected to the receiver. So when the radar transmits, the switch is in this position, boom, the pulse goes out. Then this switch drops down to receive, and it listens for echoes coming back in. And so when we run our tests, we may or may not have this radar transmitter itself running into a dummy load. But once this thing switches over here, we actually break the waveguide, it's usually waveguide, between the TR switch and the rest of the receiver. We literally break it apart. We had one guy who complained that we were breaking his radar. I think he called her Laverne, and he got really angry about it. He said, "You're breaking my radar." And we then, on our side of the break, we insert a directional coupler with a combiner. And then into the combiner, we can put in our interference, which goes on one side of the combiner, then into the coupler, and then the target generator that generates the desired targets, also into the combiner, also going into the coupler. Now, I kind of misspoke just now. Typically, the coupler is part of the radar. But if it's not part of the radar, we'll put a coupler in. The combiner is always ours. Then this right here marks the beginning of the radar receiver. Most radars, all radars really, do have an RF filter, typically a bandpass filter. So we come in through the RF filter with both our interference and our desired targets. Then we go through the front-end low-noise amplifier. This may be a number of stages, but we've drawn it here schematically as one. We go through the down conversion stage, again, usually multiple stages, but we're just simplifying it. Then we go into the radar IF. We monitor the radar IF with our spectrum analyzer so that we can verify that we're getting our signals in, and so that we can also calibrate the level of the interference in the receiver right here with the spectrum analyzer. And the radar doesn't know that this is here. The radar, on the other hand, does pass the energy of both the interference and desired targets from the IF into its detection stage, and then this goes into the planned position indicator or whatever output monitor this thing has. We have done some live targets where we actually did inject interference, where it did inject interference here, but where we did not have a target generator. Rather, we had actual echoes coming in from actual aircraft out here. We worked against that. We've also had cases where both of these, where we had the target generator set up and we're running targets in, but where we put our interference generator out here in space and radiated the interference in which case, of course, we connect the waveguide disconnect. But generally, our measurements were done this way. The trick with any operational radar, as I say, is to figure out how you really want to actually set this up and make it go. Here's the actual radar station. Here's what you're confronted with when you walk in. Here it is. Where are you going to plug in? Okay, well, so that takes a day to figure out what you're going to do. But this is something where this is all of our equipment set up over here. This is our spectrum analyzer being used to monitor the IF of the radar. This is a data gathering computer that we have. This is the equipment over here that we have for generating both the desired targets and the pulses. Now that we're using vector signal generators, since this photograph was taken, we've actually been able to significantly reduce the amount of equipment that we have here to generate targets and interference. The ideal way to do this, to go back one slide by the way, is to use a vector signal generator to make the interference and use another vector signal generator to generate the targets. That shrinks most of the equipment on this table down to basically 2 VSGs. It's a little more complicated, but roughly that's it. And again, with a spectrum analyzer to monitor the radar IF, and then a computer for taking various types of data. Now, we have to calibrate the interference level. I alluded to that a moment ago on the block diagram. This is how John likes to do it.
Wrenching experience.
It's a wrenching experience. Thank you, Bob. Here's the better way to do it. What we do is we monitor that radar IF, and we inject either the interference modulation, which might be CDMA, TDMA, BPSK, QPSK, etc., in which case it's got a pretty high duty cycle, or if we're replicating a different type of radar, we'll actually inject pulses. And we actually run the interference up to a sufficiently high level that we get to where the interference to noise ratio is just about equal to the I plus N over N ratio. And although I said earlier they converge at 10 dB, just for good measure, we go up to 20. We run them all the way up there so we don't have to do any any conversions at all. So when we see a level of plus 20 coming out of the radar receiver noise on the spectrum analyzer, then we know that whatever level that is on the VSG output for the interference, That's giving us plus 20 out here. Now we just use the step attenuator function in the VSG to step our way down to other levels that are difficult or impossible to measure directly. For example, if we want to get to a 0 dBi over N, we drop the level on the VSG by 20, we're at a 0 dBi over N, and we'll actually look at that to verify that we do see the interference 3 dB out of the noise. And we will, and we do. But if we have to work down here at minus 12, minus 14, minus 6, we can't see that directly with any kind of real measurable delta change in the IF. But we know we're okay as long as the attenuator function in the vector signal generator is linear, and we can verify, and we do verify that separately. So basically, calibration is not, it's a little bit time consuming, but it's not terribly hard. So given that this is our procedure, where did we go? What radars did we look at? Well, we looked at several of these maritime radars that we saw Bob Soul with up on that tower at both 3 gigahertz and 9 gigahertz, both in the United States and in the United Kingdom. We looked at 2 different models of long-range surveillance radars that operate between 1200 to 1400 megahertz, around, in other words, 1.3 gigahertz. We looked at an airport surveillance radar, which is this one, at 3 gigahertz. We looked at a fixed ground-based weather surveillance radar at 3 gigahertz, a state-of-the-art ground-based weather radar. All of these radars, by the way, that we looked at were the newest types of radars in their classes that we could get. We weren't so interested in looking at the older types. We did look at an airborne weather surveillance radar at 9 gigahertz. And we looked at an airport surface detection radar that monitors ground traffic at 9 gigahertz. And since everybody has seen the talk that I gave just before this, everybody knows what types of radars these are. And we looked at a precision approach radar, a PAR, also at 9 gigahertz. So this is, and these measurements typically take 1 to 2 weeks at a site to get everything done, not to mention the setup time, the time to analyze data, etc. So there's a lot of work that goes into getting that many radars. Now, what do we get out for data? Well, what we get out are the percentage of targets counted, the probability of detection of the targets counted, where every single point you see here represents 200 injected targets relative to how many targets we counted. And we get this probability of detection as a function of this interference to noise ratio that we injected for the interference into the radar. So here we looked at a long-range air route surveillance radar. We injected BPSK, UWB 10 megahertz non-dithered, UWB 10 megahertz dithered, QPSK, BPSK of various modulation rates, and a carrier wave. The upshot of the whole thing being that, for the most part, the radars we've looked at don't care about the modulation. They usually respond about the same to all of them. To the radar receiver, it all looks like garbage that tends to mask the desired echoes, if you want to put it into highly technical terms. And here we looked at BPSK 10 megahertz radiated interference into the radar, just as kind of a sanity check. So what we get on these curves is, basically, say we're at a 0 dBi over N, so we're raising the radar internal noise by 3 dB. Well, at that point, we're down to anywhere from 0.7 to 0.9 probability of detection, where this radar was running at a baseline. Although we aimed for 0.9, we were actually at about 0.96 on this radar baseline. By the way, why would that be 0.96? I just told you we try to run 0.9. The reason is that if you change the power level of the desired targets by 1 dB, that'll go from 96 to 88. I mean, that's how much difference a dB makes to a radar receiver. And we didn't want to drop below 0.9, so we go to 0.9 probability of detection baseline, or whatever the next level is above that, based on a 1 dB step size for the power of our desired targets. So this thing has a baseline running here about 0.95 to 0.96. Basically, I could not argue, we can't argue that we're seeing any drop-off in these curves up to this point, which is minus 10 I over N. But when we hit when we hit a minus 6 I over N, which results in a 1 dB increase in the I plus N over N ratio, we start to see a bit of a drop. Now, someone says, is it a lot? Well, define what a lot is, but we do begin to see some impact. When we go on up to 0, we see significant impact. Anything from 0 on up, basically on whatever azimuth the interference is getting into the radar, you can't count on seeing any targets after that. I mean, we're dropping down here to PDs on the order of 0.5, 0.4, 0.3. It's over as far as I'm concerned. Oh, and by the way, if you ask a radar operator how much interference can you tolerate, they of course will say none. That would imply that if anything, we ought to have an I over N criterion ratio criterion for this radar that would be around about a minus 10 or below for any non-radar signals getting into this radar. Now, people will say, well, how much does this reduce the radar range? Well, that presupposes that we're talking about an actual range reduction. If all radar targets had an identical cross-section, then you could argue that a range reduction would occur. But of course, radar targets don't all have identical cross-sections. Cessnas have different cross-sections from 747. Small boats have different cross-sections from supertankers. So what we see is that target losses can occur at any time in that echo listen period, and that means that target losses can occur at any distance from a radar. The problem that you're facing is not a range reduction per se, although you can convert all your numbers into range reduction if you want to use a standard target size that you basically make up as a mathematical fiction to make your analysis easy. But as I say, where you could do that, given that target cross sections vary enormously, we haven't thought that the concept of range loss in radar is all that informative. You can do it mathematically if you want to hold all your cross sections equal mathematically, but basically a small target can disappear close in and a big target could disappear further away, but any target can be lost during that echo interval. By the way, this is a maritime radar display, 9 gigahertz maritime radar display, which is experiencing interference at about a plus 3 dBi over, and so we're hitting it awfully hard at a 1% duty cycle, and all these little strobes, these are strobes, are due to the interference. Now, we were injecting interference here 360 degrees around the radar. Typically, interference is going to come in on a single radar azimuth when the main beam of the radar aims toward the interfering source. But this shows you what you would see on any given azimuth of a radar. Even if we're getting interference on one azimuth, you could see something that would look more or less like this on any azimuth. And there are 10 desired targets here, but you can't find them. The real question it comes down to is, can anyone decide which targets they would like various radars to be able to lose at which ranges? And of course nobody can. Now, although you can blow out the radar with a high I over, and we'll have some more pictures of that in a minute, and it's spectacular, not to mention fun to do that. The more insidious problem occurs when the interference noise ratio is low, something on the order of, for example, 0, -3, even -6. Where you put in a high duty cycle signal, something that might, for example, be a comm signal of some sort, because here's what happens. This is an air route surveillance radar display where we injected 10 desired targets indicated by the arrows, 10 desired targets in a row, and the cathode ray tube update cursor is spinning here, and this is not interference. This is just a photographic artifact of that cathode ray tube cursor, which is just refreshed on these targets and it's continuing to spin around here. It's a long duration time exposure, so we just had to let that cursor make an arc here. What we're not seeing, I emphasize we're not seeing, is any interference effect due to the signal that we're injecting. All we see on the azimuth of the targets, and we're injecting the interference here only on the azimuth of these targets, so we're having the interference pop on and then disappear when the radar beam, as it were, scans over the targets so that the radar sees the interference the way it would see interference from a distant point source in space. We see no interference artifact on this azimuth of the targets. But we're missing 3 targets, and because we're at a 90 to 95% PD for this radar, we should have seen 9 to 10 targets, and we did when we didn't have the interference on. So what do you see where the targets are missing? Nothing. Absolutely nothing. And if you were an operator and you saw nothing on a radar screen, let's say, oh, here, what would you conclude? There's nothing there. What if you see nothing here? Well, there's nothing there. Oh, but we know there was a 90% PD target there that we injected. So this means that low-level interference can cause a very insidious interference effect, which is that it can cause a target to disappear without any ancillary effect on the screen, on the PPI scope, to indicate that anything has gone wrong. Here is a long-range air-out surveillance radar display where we are injecting the interference 360 degrees around, but it's a long story. We fool the radar into thinking that it's only looking at one azimuth, even though it is in fact looking around 360 degrees around to see the interference. We were injecting 25 desired targets all around, and the desired targets are spaced evenly. And every target we observe has been drawn in here with Photoshop with a yellow arrow. Every target we're missing has been drawn in with Photoshop with a red arrow. So you don't get to see the red and green, the red and yellow arrows on the actual radar display. We fake that part, of course. And here's what we see. All the yellows are the detected targets. That's good. And again, the baseline was 90%. But we're missing 1, 2, 3, 4, 5 targets on this scan of the radar. So we're missing a fifth of our targets. And this was with injection of a BPSK type signal at a low interference to noise ratio. And again, what do you not see? You see no indication of any interference effect on any of these azimuths. You just don't see the target. So again, this is an indication of how subtle and insidious the effects of interference can be on a radar at low levels. It also means that if someone says, oh, and this has happened, people other than us have done certain tests where they have said, well, we turned on interference and the operators of the radar didn't see any problems, so we assume that we can operate in this band with the radar. Well, here's the problem. The operators won't see any problems unless you turn up the power level of the interference to a really high level. So the operator will say, yeah, looks good to me, screen looks clear, because they're typically not injecting any desired targets when they're doing that. They're just looking at targets out in space, and they can't keep track of which is which. Here's a maritime radar display when we boost the level of the interference to a little higher level, I over N of plus 2 dB with a QPSK signal. And here, all this speckling in here, that's all being caused by the interference. These are 90% probability of detection, desired targets on a radial, and at best you could probably pick out 1, 2, 3, 4, 5 of those. And by the way, the person who did most of the counting with his eyeballs was me. That got us consistency from one radar to the next, and I bent over backward to declare targets when I could. I would count 5 targets. We tried doing this with automatic target counting software, and under a circumstance like this, the target counting software said 0. Okay, so I was bending over backward to find the targets. That means that those I over N curves that you see are optimistic in terms of the good behavior of the radar, because that was with me watching and saying, oh yeah, I'll count 5 there. Whereas I say software that would try to count these automatically it performed miserably relative to what a trained human operator can do. The only reason they use software, as far as I can tell, is it saves on training costs.
Well, that's a very difficult
It's
problem.
a tough thing to pull out. You have to get used to how the radar works. I would usually take a couple hours to get used to how the radar works and how the targets would. But right, having Bob, yeah, I agree. Having software declare, pick that out of a background speckle. Right, that's where you hope that the frontal lobe of the human brain works better than somebody's
you have a pretty
code.
powerful processor.
Right. Well,
yeah.
some more powerful than others, but
We won't go there.
we won't go there. Right. Now we did do some where we just blew out the radar display just basically for fun. Long-range air route surveillance radar, maritime surface search radar. This is like what you might see in the movies. But one thing about this kind of blooming, first of all, if you hit a radar this hard, it would probably only show this on one azimuth because it'd be a point source located at a distance from the radar. But on that azimuth, you'd see a slice of this interference occurring out there. But the other thing is that if an operator sees a big old strobe or some kind of interference blooming on the scope, at least they know there's something wrong with that azimuth, and they can say, hey, I'm blocked out on that azimuth. There might or might not be a target there, but they know something's wrong, as opposed to the problem where they see nothing on a given azimuth, no interference effect and no target. So they're just, they're fat and sassy. They're happy. They think everything's wrong. Now, what about radar-to-radar interference? Everything we've looked at up to this point on these scope pictures and the data curves has been virtually 100% duty cycle signals getting into the radar. Well, here's what happens when a radar signal gets into the receiver of another radar that's sharing the same band. If a feature called interference rejection is turned off, then the radar interference can generate these tracks on the scope. It can also create some of this ancillary speckling that we see here. And this is a maritime radar display. But you can flip a switch that's titled IR, interference rejection, turn this feature on. And I'll tell you in a second what this feature really is. It turns out it's actually a pretty quick and dirty feature, but it works well. And interference rejection will eliminate almost all of the effects of interference when it's turned on, if the interference has a sufficiently low duty cycle. And when interference rejection is turned on, we were able to run up to interference noise ratios as high as plus 30 and by accident one time plus 60 dB, and the screen still looked like this. Now, You do pay a little bit of a price in interference rejection in terms of your ability to detect some targets. But basically, here are 10 desired targets, which are also being injected on this display, and the difference is dramatic. Here, the 10 targets come right out, no problem at all. So what is interference rejection? Interference rejection is implemented down at the video level in a radar receiver. There's a threshold comparator, and coming out of this threshold comparator, the signal, and this is the echo energy that's being integrated to make targets, gets split into two lines. One line has, we'll call it zero delay. The other line has some non-zero delay. And we run these into an AND gate. So if we adjust the delta delay here to equal the time interval between the transmitted pulses that this particular radar is firing into space, then, because the echoes have to come back with the same time spacing between them for a given target, the AND gate will pass a voltage out, and that can be integrated to develop a desired target. But if there's another radar in the band, and assuming that the other radar in the band that is putting in what amounts to interference energy is operating with a, and this is key, a different pulse repetition interval from the pulse repetition interval of this radar. In other words, if you call this the victim radar, this victim radar has a different pulse repetition interval in its transmitter than some other radar that is gratuitously injecting interference into it. Then the time delay, which is equal to the pulse repetition interval, will not end up putting the input on the two sides of the AND gate at the same time. Nothing gets passed through, and that's how we get this fairly dramatic improvement when we turn on interference rejection. But interference rejection only works up to a duty cycle we found of about maybe 1% to, if you want to be optimistic, maybe up to 3% for interference. When the interference duty cycle goes over about, and we have to say about, we have to explore this more, we don't know for sure where this lands for every radar. When the interference duty cycle exceeds about 1 to 3%, then this approach to eliminating the interference effects on the scope display begins to break down. In fact, it breaks down pretty fast. This also means that, to go back to the solid state radars, if a solid state radar has a 10% duty cycle, then another radar may, and in fact not may, it will, we've seen it, will end up getting its energy in through this interference rejection circuitry, and now you will get some interference from one radar into another radar when some of the radars are these real high duty cycle solid state radars that have these 1 to 10% duty cycles in their transmitters. But in particular, of course, NTIA is worried about what will happen if we're trying to share a radar band with non-radar signals, because all of these various communication signals are, virtually 100% duty cycles. So, briefly, in one graph on one slide, here's a summary of the results for all these different types of radars. Long-range radar number 1, long-range radar 2, long-range air search radar. Oh, I'm sorry, I misstated. We did radar 1 at 2 different installations, 2 different places in the country, and in long-range radar 2, right? So 3 radars, but 2 types of radar. Short-range radars, fixed ground-based Met radar, and various maritime radars, airborne Met radar, etc. Well, we tend to get pretty similar numbers. We start to see the PD drop off on all these radars at -9, -9, -6, -9, -9. So there's some consistency in here. The meteorological radar now has improved signal processing software, which has made it actually vulnerable at I over N levels as low as -14. Predicted. We haven't measured that. It's predicted. And then we get into the maritime radars, the surface search radars, -7, -10, 6 to 9, etc. So we see a fairly consistent story. Putting aside the meteorological radar that may be anywhere from -9 to -14, we see typical thresholds where we start to lose probability of detection anywhere from -6 to -9. If we were to develop an interference criterion for high duty cycle signals, we would probably go with -9 as a safe place to start. So, in summary, interference at high duty cycles, here meaning anywhere from 1 to 3%, where the interference rejection circuitry begins to break down, typically does cause target losses to begin at levels anywhere from -6 actually to -10 if you look at the totality of all our data. But we could probably even work with, again, -6 to -9. Interference at low duty cycles, when the duty cycle interference is less than 1 to 3%, that can allow you to sustain I over N levels as high as +30 to even +60 without degrading the radar receiver performance. What this really says is radars live pretty well with other radars in a band. Radars don't live well with non-radar signals in a band. Target losses due to low levels of interference, this is levels of interference like 0, -3, -6, are insidious because they don't produce visible interference effects on radar displays, but they can cause desired targets to simply fade out and not be seen at all. And although we can mathematically develop a radar range reduction, if we want to hold radar cross sections arbitrarily equal to each other, mathematically speaking, in reality, any radar target can in principle be lost at any range if the target echo power is close enough to the radar's noise floor that the interference wipes it out. But this means that losses won't just occur at the edge of radar coverage. They can occur anywhere on a radar scope display if the target echoes are close to radar receiver noise. So again, that means a small cross-section target close in or a big cross-section target that's far away. What are the implications for spectrum sharing between non-radar systems and radars? Well, to the extent that these communication type signals, typically nowadays digital signals, QPSK, BPSK, etc., have high duty cycles, that means that if we're doing electromagnetic compatibility studies, we would want to work with I over N thresholds for interference for compatibility and coordination studies that would be set at probably -6 to -10, depending upon which radar you want to pick. We have, here at NTIA, demonstrated the workability of dynamic frequency sharing, dynamic frequency selection, with wireless local area networks, also known, basically the same as radio local area networks, WLANs, RLANs, in the 5 gigahertz band. These DFS devices have been implemented commercially, they're sold commercially. But the whole point of how they share with radars, which is developed in ITUR M.1652, is to limit the interference level from these DFS devices into radar receivers to I over N levels that are in fact below -6. The whole criterion was written to keep these RLAN devices from getting more than an I over N of -6 into various radar receivers. And there are a lot of gymnastics that are involved in how these DFS devices work to try to ensure that that happens. People have talked about extending the DFS concept to other bands and to other radio technologies like IMT 2000 or now WiMAX at, for example, 3 gigahertz. To the extent that these could be attempted, they're going to require the development of new and different sharing protocols. It's not a matter of doing a cut and paste out of M.1652 into some other protocol. The reason is twofold. Number one, radars at 3 gigahertz have somewhat different characteristics in terms of their pulse characteristics from 5 gigahertz radars. So the radars differ. Second of all, the functionality of IMT 2000 and WiMAX is not the same as RLANs or WLANs are. So that's why an entirely new sharing protocol would or will need to be developed if people want to extend these different types of radio technologies into a band that uses different types of radars. It's not just a fast cut and paste one size fits all. As far as future radar interference studies goes, we ourselves do not understand well what happens in the regime from about 3 to 5% duty cycle, or even from about 1% up to 5% duty cycle. This is where we transition from interference rejection working well to interference rejection not working at all. And we don't understand and we don't know what happens right in that regime, so we'd like to look at that. We'd like to explore that regime more. There are some additional types of radars we'd like to look at. So we're looking for sponsors for this work. So whoever might see this talk when they dig this out of some ruin underneath a future civilization, we are looking for sponsors for this work, if you can still get back in touch. And if you want to read more about this, there's an NTIA report, TR 06-444, Effects of RF Interference on Radar Receivers, that can be downloaded from this URL, which provides a lot of the additional background information that people might want on this. And then finally we have the various acknowledgements to different people who helped us out with all this work. In the United Kingdom, the Coast Guard Maritime Agency, the Fraser Range in England, Sperry Marine, Calvin Hughes, Northrop Grumman, the FAA, the U.S. Coast Guard, the U.S. National Weather Service, U.S. Air Force, the Air Force GPS wing, and this was, of course, a joint effort with NTIA Office of Spectrum Management. So we've still got at least 10 minutes to take any questions and answers before the tape runs out. But this concludes the formal part of the talk at this point. Any questions? Bob?
On that figure where you showed that the targets dropped out,
Mm-hmm.
was your IR on or off? Interference rejection on or off?
Ah,
Because it was fairly clean there. for the
Yes.
stuff you had.
okay,
I was
cool.
wondering
Right.
if maybe the interference was upsetting the interference rejection rather than the
Right.
detection.
Are you talking about this figure here, for example? Yeah.
That's rather clean, so it looks like
Right, good
IR
question.
is on.
That's a good question. And so the question is, was IR turned on? In effect, IR was turned on. Now, there's a slightly different implementation of interference rejection on this type of radar, and it's called CFAR, which is Constant False Alarm Rate. It's a different implementation from the IR circuit that I showed you, but its effect is the same. CFAR is an averaging function, which allows you to basically average out slight variations in noise, or for that matter, if you had interference occurring, it will tend to average that out. CFAR has the effect of reducing clutter on radar displays when interference is not present, and when interference is present, CFAR has a tendency to reduce the appearance of interference. If you run up the interference level high enough, it'll finally get through even the CFAR, the constant false alarm rate filtering. But yeah, CFAR, which is the equivalent of interference rejection, was turned on here. We normally did have either interference rejection or CFAR turned on and implemented whenever we did a test, because first of all, most people who use radars do use the radars with those features turned on. There are some purists, including one famous radar design person who we talked to, who said, CFAR is a crutch. He sort of seemed to be questioning the manhood of anybody who would actually use it. But the fact is that most operators do turn it on. He said a person who really knows how to use a radar display doesn't need it. But it was turned on, so yes, Bob, it does tend to smooth this out and average it
So is
out.
the baud rate of the BPSK signal comparable to the pulse width of the radar signal?
That's a good question. Is the baud rate?
I'm just trying to figure out
is the baud
why-
rate comparable?
Why would it make it disappear? It's adding power, which, you know,
I was wondering if it adjusted the threshold, if somehow the radar was adjusting its threshold.
Ah, well, Mike. Okay, I think you're getting more at it, Mike. Mike said maybe the radar is adjusting the threshold. Here, I'll go even a little deeper into it. I didn't want to get too far into too many details for the talk, but that's actually worth getting into. The CFAR function has the effect of raising a processing threshold. And in fact, the downside of using CFAR is, and I'll go back to this, the downside of using CFAR is that CFAR will also eliminate a really, really weak target that otherwise would have been seen. But by turning on CFAR and reducing the clutter, you pay the price in losing a really weak target, but you clean up the clutter display situation enormously, so you get a screen that looks like this. But I think, Mike, that your comment actually comes closer to it in terms of why that effect occurs than looking at the BPSK chip rate. Here you can see, Bob, that we use BPSK chip rates ranging from 0.5 to 1 to 5 to 10 megahertz. And they've all got roughly they've all got the same effect on the radar. But yeah, in terms of how that works, I think a better answer is that the CFAR has the effect of ever so slightly raising that processing threshold due to this averaging that the CFAR does on adjacent range and azimuth cells in the radar processor.
but then you said as you turn the interference up, this effect would go away.
Yeah, there are
So
levels.
Why would it change, you know,
Oh, there are.
with setting the threshold, the CFAR algorithm?
Yeah, why do you finally see strobing coming through? I can only tell you qualitatively. Quantitatively, I can't answer the question. Qualitatively, that interference power becomes so high that it actually generates an actual hardware strobe. If you've got a PPI, now this is an artificially generated computer display, and I'm not sure how the computer is actually processing to generate these strobes, but on a display like this is an actual analog display where there is an electron beam, which we see here, which is actually scanning around. You eventually get that interference power up so high that it's actually finally causing the deflection on this beam in terms of energy being transmitted to the phosphor on the scope to actually come through and actually light up the phosphor. I can't give you a quantitative answer right at this moment, but qualitatively, you finally run the level up so high that basically your signal processing becomes irrelevant. The radar signal processor has nothing to do with it. It's you're actually running the video energy in the radar receiver up to some voltage limit, and it's just passing it through as just some voltage level that's just held high apparently.
So Frank, do you actually, to generate these targets, do you actually record the waveforms and then just inject them back into the system, or actually have?
Oh, question, yeah. To the targets or the
targets.
The targets. Okay. What we do to generate the targets. The question is, how do we generate the desired targets? What we do to generate the desired targets is to get the radar's pulse repetition interval, and we can either get it off a spec sheet or better yet, we'll actually measure it. And I'm going back here to show what happens. And we actually generate energy out of a vector signal generator that has the same modulation as the radar pulses. So if it's a simple radar, it's just CW modulation. If it's a more complex radar modulation, we can replicate that modulation. But what we do is we actually generate echoes with a time spacing between the echoes that equals the time spacing between the radar's transmitted pulses. We replicate with the vector signal generator whatever modulation the radar might be using on the pulses. Okay. And we inject anywhere from 10 to 15 to 20 of those in a row at that repetition interval, and then we turn it off for an interval time that's equal to the radar's antenna scan time. So for example, suppose that we have a radar that has a 5-second scan time. That means that every 5 seconds into the receiver, we fire 10, 15, or 20, whatever the radar's criterion is for declaring a good target, 10, 15, or 20 echoes at some level that we run up and down until we hit a 90% PD, with an interval between the echoes equal to this interval between the transmitted pulses, and then boom, we shut it off for another 5 seconds. So now the radar thinks that it is in fact seeing 10 or 20 actual echoes from a real target on some particular azimuth. And if we're going to put multiple targets in, and I'll go forward here, if we're going to put multiple targets in on a radar display like this, for example, here we're generating, I'll call it 10 for the sake of argument. We're generating 10 echo pulses there. We generate 10 echo pulses there, 10 echo pulses there. So these are being generated as little groups of 10 in a short interval when the radar antenna would be aimed just in that direction. And then we inject another set of groups of 10, 10, 10, 10, 10, 10, 10, 10, 10, on this next radial like that. So here we're going nuts in terms of generating these. But just bear in mind that every single one of those blips is 10 echo pulses, or 15 or 20, depending upon what the radar's design criterion is for declaring a good target. And here on this radar display, we're doing the same thing. Come up to it here quickly. And we're just about out of time on the tape, so we'll probably have to cut it off here. But yeah, here again we're generating 10 echoes real close together, then 10 echoes, 10 echoes, 10 echoes, 10 echoes, and each of that set of 10 echoes makes a blip on the screen. But the groups are occurring so close to each other that they look like they're all on the same azimuth or the same radial here. If we want to generate a ring of targets, then we do the same thing, except we generate 10 here, and then we wait and we generate 10 echoes there for the next target, then we wait and generate 10 echoes there for the next target, and wait and generate 10 echoes there, and so forth on around. But we use whatever the radar's design criterion is for how many echoes.
Now, will you always have your waveform information, or do you sometimes have to take a recording or get a record to figure it out?
We've always had the waveform information. We could, in principle, do a recording with the vector signal analyzer and play it back with the vector signal generator, but so far we've always just gone with the nominal spec for the radar, and we haven't had to actually do a recording. So the tape's about to run out, and Bill Ingram can cut it off here at any time. But if there are any other questions, you can go ahead and ask any other questions. But again, that concludes today's talk. Thanks very much for coming.